Well, I needed to make a solution guide, and based on the way today went, at least a few of you still have some questions, are not confident, however you want to say that. So, I don't know, grab a pencil, copy down what I say, and ask some questions tomorrow. A particle moves along the x-axis so that at time t is greater than 0 hours, its position is given by x of t miles. At t equals 0, is the particle moving to the right or to the left? This is about velocity. So the first thing we want to do is write that velocity is the first derivative of position. So we want to make that connection. So velocity is 3t squared minus 6t minus 9. And then we're just going to do v of 0, which is negative 9. And then we conclude, since v of 0 is negative, the particle is moving left at t equals 0. That's the shortest I think I can do. At what time does the particle change directions? Well, this is a question of if the particle is moving left, the velocity is negative. If the particle is moving to the right, the velocity is positive. So this is asking, where does the particle change sign? Where does the velocity change signs? Oh, shoot. I need to do slightly more work. We're going to let the velocity equal 0. So 0 equals, is it 3t squared? Yeah, 3t squared minus 6t minus 9. And so 0 equals 3 times t squared minus 2t minus 3. And we could drop the 3, but maybe I won't. So t minus 3 and t plus 1. So t equals 3, t equals negative 1, but don't forget the domain way back at the beginning. We were told t is greater than or equal to 0. So I'm going to make a sign chart. We'll use it again later. The domain does not extend left of 0, so we'll just keep that. These are t's, and this is the sign of v of t. So v of 1 is, well, 3 minus 6 minus 9, definitely negative. And then if I use 10, that'd be 3 times 10 squared 100 minus 60 minus 9. Definitely positive. So we're going to say at t equals 3, v of t changes signs. So the particle changes directions at t equals 3. All right. So at t equals 1/2, is the velocity increasing or decreasing? Remember, increasing means the derivative of something is positive. Can't spell. So this is asking, is the derivative of velocity positive or is the derivative of velocity negative? Okay. So let's see. The first thing we need to do is get acceleration, the derivative of velocity. And I'm going to say acceleration as a function of time is the first derivative of velocity. So acceleration is, let's see, the derivative of 3t squared is 6t. The derivative of minus 6t is minus 6. And the derivative of minus 9 is 0. Make sure I did that all correctly. 6, 6. Okay. And so now we'll just do a of 1/2, which is 3 minus 6. And I'm not going to bother evaluating, even though that's negative 3. Because now I can say a of 1/2 is less than 0. So at t equals 1/2, the velocity of the particle is decreasing. All right. So you may have thought in part C that you should have done what we're about to do here. So it asks, at 1/2, is the speed of the particle increasing or decreasing? Another way to say this is the particle speeding up or is the particle slowing down? Right? So even though speed is the absolute value of velocity, we actually just need, let's see, the velocity evaluated at 1/2 and the acceleration evaluated at 1/2. Oh, we already have that. At 1/2, the acceleration is negative. And, oh, we have evidence up here. At 1/2, looking at this sign chart, at 1/2, the velocity is negative. Oh, so that means velocity, acceleration are working together. Okay. Now you could go ahead and say v of 1/2 is equal to, whatever, but we can use that sign chart. So let's see. V of 1/2 is negative, and a of 1/2 is negative. So at t equals 1/2, the particle is speeding up. Oh, sorry. We want to use these words. The speed of the particle is increasing. All right. Find all values of t for which the particle is moving to the left. We need to know when the velocity is negative. Oh, didn't we already make a sign chart for velocity? We sure did. So let's see. The velocity is negative from 0 to 3. Now we're not going to include t equals 3 because at 3 the velocity is 0. But at 0, let's see, that'd be 3 times negative 3 times 1. That would be negative. We will include 0. Okay. So let's see. On 0 to 3, v of t is less than 0, so the particle moves left on 0 to 3. And unlike increasing and decreasing, we won't include that t equals 3. Just because, what would we normally say? At t equals 3, the velocity is equal to 0, so the particle is at rest, so we don't want to say the particle is moving left at that moment. Kind of a weird bit. Okay. What is the particle's acceleration at t equals 1/3? Explain with units the meaning of your answer in terms of the particle's velocity. So I already know it's going to be a change in velocity. Right? Because acceleration is by definition a change in velocity over a change in time. So I'm already thinking that. And we might as well go back. Let's see, what's acceleration? Acceleration is 6t minus 6. And the acceleration at 1/3 is 6 times 1/3, or 2 minus 6. Which is negative 4. And then it did say using correct units, so we need to go back. What are our units? Let's see. Oh, it's miles and hours in this situation. By the way, in case you're curious, let's see. Maybe we should put these in. This velocity of -9 is -9 miles per hour. I don't think we had any positions, but the position, like if we did x of 1, that would be 1 minus 3 is -2, minus 9 is -11, plus 2 is -9, and those units would be miles. So every time we take a derivative, we're going to get a per hour in the denominator. So the position is in miles, the velocity is in miles per hour, the acceleration down here is in miles per hour. Okay. So how can I try to explain what this means? At t equals 1/3, so at the 20-minute mark, let's see, the velocity, well, is the velocity growing, shrinking, or staying the same? Well, the velocity is shrinking. Maybe I'll say decreasing. That sounds fancy. The velocity is decreasing at a rate of 4 miles per hour each hour. Which I guess means at this rate, if we waited an entire hour, so give a denominator down here, right? That's in 1 hour, the velocity would decrease by a total of 4 miles per hour. I hope that makes sense. Okay, so, with these, maybe we just work on translating, memorizing, I don't know. So if velocity is negative, so the particle is moving left, and acceleration is positive, then speed is, well, that's decreasing. Right? The acceleration is working against the velocity. So if the velocity is positive, so the particle is moving right, and the speed is decreasing, well, that means if the speed is decreasing, the acceleration has to work against velocity, so acceleration is negative. Be careful here. Some of you might mix up negative with decreasing and positive with increasing. Okay, so let's see. The velocity is positive, the particle is moving to the right, and the velocity is decreasing. Ooh, I think this is the time to do some symbols. Okay, so velocity is positive, v of t is greater than 0. And then it says the velocity is decreasing. So that means the derivative of velocity is negative, which means the acceleration is negative. So let's see, the velocity is positive, the acceleration is negative, speed is decreasing. Okay, if speed is increasing, which means acceleration and velocity are going to be both positive or both negative. Let's see, if speed is increasing, acceleration is negative, velocity is matching. I was going to write velocity. Velocity is negative. If velocity is negative and velocity is increasing, so v of t is less than 0, and v prime of t is greater than 0, so acceleration is greater than 0, then the speed is decreasing. All right, if the particle is moving to the left, so v of t is less than 0, the speed is decreasing, so velocity and acceleration are fighting each other, then acceleration has to be positive. Hope that helped. All right, I think this is the last one, right? So the graph above shows velocity. I'm a fan of rewriting that, just so I don't forget, in miles per hour. And I know that says it very small, but maybe I write it here, miles per hour, of a particle moving along the x-axis for 0 to 11 hours. It consists of a semicircle and 2 line segments. Use the graph and your knowledge of motion to answer the following questions. At 0 to 11, at what time is the speed of the particle the greatest? So speed is the absolute value of velocity. And so I guess one way to think of it is, at 0, at 4, at t equals 10, the velocity is 0 and the particle is at rest. When is the particle farthest away from that situation of being stopped? And it's right here when the velocity is -6. So at t equals 8, the speed of the particle is the greatest. Right? The magnitude of the velocity is the largest. Velocity is the farthest away from the x-axis there, something like that. At which of the times, 2, 6, or 9 hours, is the acceleration of the particle the greatest? Well, what does acceleration mean? I think you can say, well, acceleration is the derivative of velocity. And we have a velocity graph. So we're actually talking about the slope of the velocity graph. So this is actually asked relatively frequently in different forms. So 2, 6, and 9. So let's see here. At t equals 2, a of 2 is equal to 0. That's a horizontal tangent. That's pretty easy to see. The slope of this graph at 6, 3, 4, 5, sorry, 6, let's move that over, is negative. So I at least know, I forget, greatest or smallest? Is the acceleration the greatest? Okay. So I at least know that at 2, the acceleration is larger than the acceleration at 6. And then the last one is 9, I think, maybe 8. Doesn't matter. Oh, definitely not 8. Let's see, and the acceleration at 9 is greater than 0, for sure. I'm not even going to bother calculating the slope of that line segment because I'm just comparing it to a negative number and a number equal to 0. Okay. So let's see. How do we explain this? The slope of v of t is positive at t equals 9. The slope of v of t equals 0 at t equals 2. And the slope of v of t at x equals 6 is negative. So acceleration is greatest at t equals 9. Okay. Over what open time intervals is the particle moving to the left? So what we're looking for is velocity is negative, and this is a graph of velocity. The velocity is negative from 4 to 10. Okay. So let's see. On 4 to 10 open interval, v of t is less than 0. So the particle moves left. On 4 to 10. Make that look a little more parenthetical. Over what open time intervals is the velocity increasing? Oh, that's really easy. We're going to look at where this graph, the velocity graph, increases. Where does this graph increase? From 0 to 2 and from 8 to 11. So, the velocity increases on 0 to 2 and on 8 to 11. I guess we say because velocity graph increases on those intervals. Okay. You would never actually have to justify that because your justification is the exact same as the conclusion. But whatever. I guess we're not given hints here. Over what open time intervals is the speed of the particle increasing? So 2 ways to go, and I'll do the more thinky one first so you can, not know the conclusion ahead of time. So remember, the first thing I said here when we looked at this graph was, or at least one of the early ones, pen stopped working. When the velocity is equal to 0, when this graph crosses the x-axis, the particle is at rest. Okay. No, I didn't want blue. I wanted red. Okay. So at 0, at 4, and at 10, the particle was at rest. And so if the particle is at rest and then is not at rest, meaning right afterwards in terms of time, well, that would mean that the speed is increasing, right? And so you can just kind of think, well, speed is the absolute value of velocity. Where is the speed increasing? Where the velocity graph gets farther away from the x-axis. Apparently I've been talking too long. My pointer has run out of juice. Let's see if this one works. Oh, it does. Okay, always have backups. Now the other way to go is to just draw the absolute value graph. The absolute value of velocity is going to be identical to velocity, where that velocity is positive or 0. And then try to eyeball that. So now I can just look at this graph, and where is this graph increasing? Well, where the graph increases, where for the larger x value, the new y value is higher. So that's from 0 to 2, from 4 to 8, and from 10 to 11. Let's see. So on 0 to 2, 4 to 8, and 10 to 11, the speed of the particle is increasing. So we do kind of have to tie it back to this graph. So we know we're talking about 0 to 2. We know we're talking about 4 to 8 and from 10 to 11. But we're not really supposed to use anything other than the graph given. Okay? Now, remember, speeding up and slowing down is about velocity and acceleration. Okay? So here's my justification. Maybe I should have done this first. On 0, 2, and 10 to 11, the velocity graph is above the x-axis, so I can say positive and increasing. And that's actually good enough, because don't forget, when I say velocity is increasing, I mean the derivative of velocity, the acceleration, is positive. So that means when I go back and let's do it here, on 4 to 10, velocity is less than 0. This velocity graph is below the x-axis, and velocity decreases. And don't forget, when velocity decreases, the derivative of velocity, the acceleration, is negative. So I'll just go ahead and rewrite that here. On 4 to 8, the velocity is negative and decreasing. Don't forget, last one, I'm just going to say it, but I don't feel like writing. When is the acceleration of the particle undefined? When the slope of this velocity graph is undefined at corners, cusps, discontinuities, or vertical tangents. So where does this graph not have a derivative? At 0, that's a vertical tangent. At 4, that's a vertical tangent on the left and between the two parts, a corner. At 8 and that's it. The last one is, we don't really have to worry about that, but the very last thing, find this area and all of that, that's as a hint as to where we're going in the next unit, but the one hint I will give you is look for the units. I'm not going to write down the result here because I want to see what you can think about. Hope that helps.